In section 5.1, we're looking at inverse functions, and our objectives here are to determine whether a function is one-to-one, and then if it is, find a formula for its inverse. We're also going to simplify expressions of the type f of f inverse of x, that's composition of a function and its inverse, and the reverse, f inverse of f of x, so composition of an inverse and the function. First, we've got ourselves a quick review. Which of these graphs could represent functions and why? So if I look at this first graph right here, I'm going to notice that it is not a function because it fails the vertical line test. In this second graph here as well, we're also going to see that it fails the vertical line test. If I was to draw a vertical line in several different places here, I'm going to see that I'm able to cross more than once. So once again, this is not a function. It fails the vertical line test. And then in the third graph over here, anytime I draw a vertical line through this graph, it's only going to pass the graph once. That's going to pass the vertical line test. This one is a function. And does pass the vertical line test. If we consider functions to be like machines, then the inverse functions are machines that undo whatever the function does. We already know lots of operations that are inverses of each other. For example, if the operation is x plus 2, the inverse operation would be x minus 2. Notation for the function and its inverse. The function, f of x, is x plus 2 in this case, and its inverse function would be the function x minus 2. We use the f inverse notation for the inverse function. Similarly, if we've got the function 3 times x, the inverse operation, instead of multiplying by 3, would be to divide by 3. So x divided by 3. So our function here is 3x, and its inverse is x divided by 3. For the square root of x, the opposite of a square root is going to be square, so the inverse is going to be x squared. So if f of x is the square root of x, then f inverse of x would be x squared. And last, the opposite of x to the power 5 would be either x to the 1/5 power, the reciprocal power, or the 5th root of x, depending on which of those two notations you prefer. So if we write our function as x to the power 5, we can write our inverse function as either of those two options. I'm going to go with the reciprocal power notation. X to the 1/5 is one way to write the inverse function. All right. On the next page, our topic here is inverses. So as we look at inverse functions, there are going to be three main ways: relation of values, aka a table, graphs, and equations. So first of all, tables here. Complete the table below for a function and its inverse. All right. So what I have first here is a set of ordered pairs for the function, and then over here it's a set of ordered pairs for the inverse of that function. In my original function, the x value is 6, and it maps to the output value of 76. So in the inverse, these are going to swap. The input would be 76, and the output would be 6, because the inverse function undoes what the function did. In the regular function, 6 mapped to 76. So for the reverse, 76 is going to map back to 6. If 7 as an input gives an output of 68, then in the inverse function, An input of 68 gives an output of 7. An input of 8 gives an output of 60, so if we're in the inverse, input of 60 gives an output of 8. And then if the input of 52 in the inverse function gives an output of 9, in the inverse, an input of 9 will give an output of 52. So if this is the function, that's its inverse, and vice versa. They're inverses of each other. Similarly, in the inverse function here, 44 to 10, so in the original function, it must have been the case that 10 mapped to 44. And then finally, 11 to 36 means that in the inverse function, 36 is going to map to 11. Okay. Property of an inverse function. For an invertible function f, the following statements are equivalent. F of a is equal to b, and f inverse of b is equal to a. All right. So in plain English, the input of a function, a, and the output of the function are reversed in the inverse, right? The input of the function is the output of the inverse, and vice versa. The output of the function is the input of the inverse function. All right, so in plain English, we can say something to that effect. The input of a function is the output of the inverse, and vice versa. Okay, so inverses and graphs. We're going to plot the function 2x minus 1, that's this function right here, and its inverse on the same set of axes. So let's first graph the function 2x minus 1. So at negative 4, this function's at negative 9. At negative 2, we're at negative 5. At negative 1, we're at negative 3. 0, negative 1, 1, 1, 2, 3, and 4, 7. Okay, so if we draw our graph, this would be the original function f of x. We graph this one by plotting each of these points, although if you notice that the y-intercept is negative 1 and the slope is 2, up 1 over 2, you can draw the graph that way as well. But the points are going to help us very quickly write the inverse function. If I swap the coordinates, if this one's negative 4 to negative 8, or 9, sorry, then I would have negative 9 to negative 4. Negative 2 to negative 5 swaps to negative 5 to negative 2. Switching my pens here on circle and ink. Now we've got negative 3, negative 1, 0 to negative 1, so negative 1 to 0, 1, 1, 3, 2, and 7, 4. Let's plot these points here. Negative 9, negative 4, negative 5, negative 2, negative 3, negative 1, negative 1, 0, 1, 1, 3, 2, and 7, 4. This is our graph of f inverse of x. All right. What do we notice about these two graphs? One of the things that I notice is that these two graphs intersect or share the value at this point right here. And that's because this point was 1, 1. So when I switched the x and y coordinates, it became 1, 1. So it's the same point. Okay. So I observe that both graphs contain the point. Would be one thing that I observe. Both graphs contain the point 1, 1. And the other is that they do seem to be symmetric, equally distant from each other across these points right here. And they are symmetric across the diagonal. This is the diagonal line y equals x, slope 1. And I'm symmetric across that point because as I switch the x's to the y's and the y's to the x's, I'm reflecting across y equals x. Okay, so I might also notice that symmetry across the line y equals x. All right, next page. As it turns out, we can always visualize the graph of an inverse function by imagining a reflection of its graph across the same very special line, reflecting it across this y equals x line. So the reflection property of inverse functions for an invertible function f, the graph of f inverse, is the reflection across the line y equals x, called the identity line. Equations of inverses. We can make use of the swap inputs and outputs nature to go from a function's equation to the equation of the inverse. For example, we could take the equation y equals x squared minus 5x and switch the variables to make it x equals y squared minus 5y, replacing y with x and x with y. Note here that stopping does not let us express this as a function easily, and we would need to solve for y in order to express this as a function. It does say graph right here. I'm going to take that word off. I'm going to talk about that real quick. Does not let us express the equation easily. Typically, a function should be expressed as y equals, and we're not really able to solve for y in that context. I'm going to just show a quick look at this real quick. One of the reasons for that is in this equation, y equals x squared minus 5x. If I swap the variables, x equals y squared minus 5y, I do have symmetry across that line y equals x. Let me just dot that. And yes, there is symmetry here, but you'll notice that the inverse defined by this equation is not a function. It would fail the vertical line test. So while it's possible to draw the inverse, it's possible to graph the inverse using technology. It is not always easy to express the equation of the inverse easily in terms of a function because it's often not a function, such as the case here. Makes a really pretty picture though, but it's not a function. The inverse is not a function, even though the original equation certainly is a function. That will pass the vertical line test. So now we look to see how we can determine if our equations will have inverses that are functions. All right, so if I look at each of these relations here, in this one I've got year as the input and first class postage stamp cost in cents. And this would be the inverse function, the reverse of this, just demonstrating that I would be going from the 29 to each of these. Okay, what do I notice what the relation is inverse in terms of their domain and range? Well, I might notice that this is a function in its original orientation because the year 1992 has exactly one cost, 29 cents, and the year 1994 has exactly one cost, 29 cents as well. So this is a function. But when I go in the reverse direction and ask in what year was the cost 29 cents, there are two possibilities. So it means that the inverse is not a function, even though the original was. So this right here is a function, but the inverse is not a function. Okay, and that's the questions that were asked at the bottom of the page. So let's go on to the next page. A function is said to be one-to-one if different inputs have completely different outputs. That is, no inputs share any outputs. In terms of function notation, we would say that if a function is one-to-one and A is not equivalent to B, then f of A is also not equivalent to f of B. So not only do we have to have each input having one unique output, but each separate input cannot share the same output. Alternatively, if a function is one-to-one, when the outputs are equal, then the inputs must also be equal. In terms of function notation, we would say if it is one-to-one, same idea, when outputs are equal, inputs are equal. So if we are one-to-one, if A is f of A is equal to f of B, then it must be the case that A is equal to B because there is no alternate input that would have given the same output. All right, so this helps us think about inverses as well. So one-to-one functions and inverses. If a function is one-to-one, then its inverse is also. If a function is one-to-one, then for each input you have a unique output, and that output is not shared by any other input. And therefore, when those outputs switch over into inputs, they're not going to be repeated. So the inverse is also one-to-one. Additionally, a function that is increasing over its entire domain, so it's increasing over its entire domain, or decreasing over its entire domain, must be one-to-one, and therefore has an inverse. Just a quick little sketch of that right here. So if I have a function that's always increasing, or I could imagine one that's always decreasing, this one's increasing. If it's always increasing, then for any different input, I'm guaranteed that the outputs are different. And so I never have a repeated output. I never have a repeated input. Therefore, both my function and its inverse will be one-to-one, and the inverse will be a function. Example 1. Given this function, how can I prove that it is one-to-one? Okay, so we can actually prove this algebraically and graphically. So let's look at both of those cases. By definition, we're going to say that if f of A is equal to f of B, we need to demonstrate that A is equal to B. So let's start with f of A equals f of B. F of A would be 4 minus 2A, and f of B would be 4 minus 2B. If we solve by subtracting 4 from both sides, negative 2A is equal to negative 2B, and then divide by the negative 2, this would lead to A equals B, which is the desired outcome in order for the function to be one-to-one. We could also prove this graphically. If I were to sketch the graph of this function, just a rough sketch right here, I'm putting the y-intercept there at 4, and I've got a slope of down 2 over 1. So it's a linear function, so I just made a real quick sketch of a decreasing linear function. I know that this is always decreasing, or decreasing over its entire domain. and therefore it is 1 to 1. So we can use the algebraic definition. We can also use a graphical definition if we're able to quickly rely on a graph here. All right, continuing on, let's consider increasing and decreasing to explain whether or not these functions are 1 to 1. In the first graph here, this function is always decreasing, so it is going to be 1 to 1. It's always decreasing, therefore it's 1 to 1. In the next example, this function is increasing on the left side until you reach an x value of 0. And then it changes direction and is decreasing on the right-hand side. So it's increasing and decreasing on different parts of its domain. Therefore, it is not going to be 1 to 1. In the next graph, this function, reading from left to right, decreases in value and then decreases in value as well. It does have two separate pieces. There is an asymptote, but across its entire domain, it is always decreasing. It's decreasing until 0. 0 is excluded from the domain. Then it decreases from 0 onward. So it is always decreasing. And therefore, it is 1 to 1. In the last one, we've got our function here, and reading from left to right, this is increasing, and then it's increasing. But then at 0, it starts its decrease, and it actually continues the decrease over here. Increase, increase, decrease, decrease. So again, we are not 1 to 1. So a little bit of variety and a couple different graphs here to show some examples of functions that are and are not 1 to 1. Recall, how does the vertical line test and work, and then what does it tell us? So the vertical line test says that if any vertical line passes through a graph more than once, then the graph is not a function. So for example, if we draw a graph like this, and we examine and note that any vertical line is going to cross just one time, this one is a function. If I look at another situation here, I'll notice that in the case of this graph, if I were to draw a vertical line, it'd be possible to draw it in such a way that the vertical line passes through the graph more than once, and so this would be a graph that is not a function. All right. Okay. The next diagram right here has a couple of pictures of a function and its inverse. So let me color code these real quick. The function is this shape, labeled here by the word function. And it's also drawn here by itself, same graph, just for a little bit of additional clarity. Only the function is drawn in that particular piece of the graph. Hopefully you'll agree that this function does pass the vertical line test. It is a function. However, when I go to find its inverse, the inverse function, that's this one, also drawn by itself over here. The inverse is going to be not a function, right? The inverse is no longer a function because a vertical line would cross through at more than one place. All right. Now we could have predicted this using the horizontal line test to determine whether a function is one-to-one. Okay, so horizontal line test determines whether or not a function is one-to-one. If I look at the original function and imagine a horizontal line, if that horizontal line is going to pass through the function in more than one place, then when you flip x and y values to make the inverse, that horizontal line flips to become a vertical line, and your vertical line is going to make the inverse not a function. So the horizontal line test will determine if our function is one-to-one. And we can say that if any horizontal line passes through a graph more than once, then it is not one-to-one. Looking back at our previous page, we had already decided that the graph of the first graph right here was one-to-one. If I imagine drawing a horizontal line in any place in this graph, it's only going to cross at one place on the horizontal line, so it is one-to-one. In this graph, a horizontal line would pass more than one time. Any horizontal line would pass more than one time, so it is not one-to-one. In this graph, again, imagining any horizontal line, no matter where you draw it, it's going to cross just once. So this graph is one-to-one. And again, any horizontal line here, I could make a horizontal line here that did cross more than once. So this one is, again, not one-to-one via the horizontal line test. All right, topic 3, finding formulas for the inverse. Step 1, we've got ourselves a function here that we're going to be working on. We're going to be working on the function f of x equals 3x plus 5. So the first step is to replace f of x with y, just to get us out of that weird function notation into equation notation. So we're going to start with y instead of f of x equals 3x plus 5. And then we're going to interchange the x and y variables. So instead of y, we'll have x equals, instead of x, we'll have 3y plus 5. Just switch the x and y. And then we're going to solve for our new y value. So I'm going to subtract the 5 from both sides. X minus 5 is equal to 3y. To solve for y, now we'll divide off the 3. going to go ahead and distribute that division. That's x divided by 3, or 1/3 x, minus 5 divided by 3, so minus 5/3, equals y. Finally, we're going to replace y with our inverse function notation, just like we had originally replaced f of x with y. Now that y is by itself, that's going to be equal to the inverse function f inverse of x equals that 1/3 x minus 5/3. Therefore, we know that the function f of x equals 3x plus 5 has an inverse function of f inverse of x equals 1/3 x minus 5/3. Note that while step 3, solve for y, was pretty simple for a linear function, it can be much trickier for other functions. We'll just need to use caution when dealing with other function types. So let's determine whether this function here is 1-to-1. And if it is, we're going to find a formula for its inverse. There are two ways to determine if it is 1-to-1. One of those ways, recall, was solving to determine if the statement f of a equals f of b is going to guarantee that a is equal to b. So we'll start here. So the cube root of a plus 2 is going to be equal to the cube root of b plus 2. If I solve this by subtracting 2, the cube root of a is equal to the cube root of b. And we'll continue by applying the power 3 to both sides. And that does, in fact, show me that a would be equal to b. So this function is 1-to-1. All right, so that's the first thing we're asked to do, determine if it's 1-to-1. Yes. Now we need to find a formula for its inverse. So we're going to start with y equals the cube root of x plus 2. And then we're going to swap the variables. So x is equal to the cube root of y plus 2. And now we're going to solve for y. Subtracting our 2, this will give us x minus 2 equals the cube root of y. Raising both sides to the power 3, we'll get rid of our cube root. And will give us x minus 2 to the 3rd power equals y. Final step, I was going to call it f, I just noticed it was called g, so let me rephrase that as g inverse of x equals x minus 2 to the 3rd power. I'm not able to distribute the 3, that would be an inappropriate step. If I could, if I really wanted to, multiply x minus 2 by itself 3 times. Definitely simpler to leave it though as the binomial x minus 2 to the 3rd power. All right, so we found a formula for its inverse. It's our second step. Okay, so topic 4, we're looking now at inverse function composition and domain restrictions. So if a function is 1-to-1, we know that there exists a unique inverse function such that if I compose the function and its inverse in either order, I get back to where I started for any x that's in the domain of f. And vice versa, if I compose, instead of f of x, I compose f of f inverse of x, I'll get back to x for whatever variable I started, as long as x is in the domain of the inverse. So, looking through this once again, in this order of the composition, we know that x has to go into the original function, right? F needs to go into the original function. X needs to go into the original function. There we go. And then the original function needs to go into f inverse of x. And because x is being plugged into f first, this is going to be true for any x in the domain of f. Similarly, for the reverse composition f of f inverse, the x value goes into f inverse first. And so this is going to be true for any x in the domain of f inverse. And we'll undo the function. So in plain English, if we plug, if we plug x into the function, we're going to get to some y value. But then when we plug that y value into the inverse function, we're going to get back to our original x value. Okay, so we're thinking about an ordered pair, x and y, where the function is going to go in one direction and the inverse function is going to go in the other direction. Okay, so I'm just going to write this out in more plain English. If we plug x into a function and then apply the inverse function, we should get the x back. We should get back to where we started. All right. So we're going to show that the function g of x is the cube root of x plus 2, and the function g inverse of x, the one I found up here, the x minus 2 to the third power, are inverses of each other using the above property. All right. So let's do the composition g inverse of g of x first. So the g inverse function will be our outer function. Into that outer function, we're going to plug the g of x function. So in place of x, we will have the cube root of x plus 2. All of that right here is in place of x. Then minus 2 and cubed. Plus 2 and minus 2 reduce. So cube root of x cubed. Cube root and cube reduce. So I get back to x like I am supposed to. We need to test in both orders. So that's the g inverse of g. Let's also do the composition in the order g of g inverse. So outer function of g, this is cube root of x. Now our x is going to be the input, the g inverse function. So it's going to be the x minus 2 to the third. Okay, so all of the g inverse function is going to go right in here for x, plus 2. The large separation underneath the cube root is a cube, so these are going to undo each other. It's going to give us x minus 2 plus 2. Again, the minus 2 and the positive 2 will act against each other, and I get back to just x. So this is a way, again, of proving that the functions g and g inverse are truly inverses of each other, because when we compose them in either order, we get back to whatever was plugged in. In this case, x was plugged in. I get back to x. Note, it says, while it worked out neatly here, sometimes we need to restrict a function's domain in order to guarantee that it's going to have an inverse function. That means that we'll need to select an interval for its domain over which the original function is 1 to 1. Okay. So I had a printing error here. There we go. Consider the graph f of x equals x squared plus 3. go through the steps to determine the equation for the inverse function. All right, so I would write this as y equals x squared plus 3, and then I would swap my variables. X equals y squared plus 3, and then I'm going to attempt to solve for y. I'm going to need to subtract that 3. X minus 3 is equal to y squared, and then we'll need to apply a square root to both sides in order to get rid of a square. When I do apply the square root to both sides, that's going to give me plus or minus. So I have both positive and negative. Square root of x minus 3 equals y. So the problem with writing down an inverse function is that I have those two possibilities. Is the inverse the positive square root of x minus 3, or is the inverse the negative square root of x minus 3? We have two options. Explain why f does not have an inverse function. It doesn't, because there were two different options. I couldn't say which one it was going to be. Okay, there is not one inverse function because we got two choices. And no way to determine which of those is true. They're actually both or neither true together. So we don't have a way of getting a singular inverse function. How can we restrict the domain as to allow it to have a familiar inverse function? All right, so the original function, x squared plus 3, parabola with a vertical shift of 3. The reason that this is not have an inverse is because it's not 1 to 1. And I can see that because my function decreases on the left side. And then it's going to change and it's going to be increasing on the right side. So it is not 1 to 1. However, if I were to cut this function at 0, then it would be 1 to 1 on either of its two halves. So this would be a picture of f of x on the interval 0 to infinity. So it's been sliced, starting at 0 to go up to infinity. It's just the right half of this graph. Has inverse. On the right half right here, this is when all of the x values are positives, right? And so since the inverse, the x's and y's switch, so the y's are the inputs, the outputs are the x values. So they're positives. So this would be the positive square root of x minus 3. As opposed to the other half. So this would be f of x on negative infinity to 0. And it would have inverse. Again, this is where all of the x values are negative, right? And so this would have inverse negative the square root of x minus 3. So the entirety of the function does not have an inverse. But if I cut it and look at it in two pieces, it's going to have an inverse on just the right side of positive square root of x plus 3 and an inverse on just the left side of negative. Typically, when we're talking about squares and square roots being inverses of each other, we're assuming it's for positive values of x. But that assumption doesn't have to play out. We could also work on it for negative values of x. So even though the typical assumption is positive, it's important to know that we could do it for both. All right, last page here. One of the most frequently used examples of inverse functions is the relationship between Fahrenheit and Celsius temperature scales. We know that 0 degrees Celsius corresponds to 32 degrees Fahrenheit, the freezing point of water, and that 110 Celsius corresponds to 212 degrees Fahrenheit, the boiling point of water. Come up with a linear function g that converts Celsius to Fahrenheit. So if 0, 32 is an ordered pair that goes between Celsius and Fahrenheit, 100, 212 is another one. If I'm going to write a linear function, 0, 32 would give us a y-intercept or b value of 32. And I can compute the slope, y2 minus y1 over x2 minus x1, so 212 minus 32 over 100 minus 0. 212 minus 32 is 180 over 100. It's going to give me 1.8, or you could write that as the fraction 9/5. So the equation that converts Celsius into Fahrenheit will be, the output value is the Fahrenheit, so I'm going to call it F. So my inputs are C's, my outputs are F's. So F equals slope of, I'll use the fraction notation, doesn't matter right here, 1.8 or 9/5, times the input, which is C, plus 32. Explain what the inverse function would do in this context. So the original function converts Celsius to Fahrenheit. The inverse function is going to convert Fahrenheit to Celsius. Evaluate and explain the following. I need to find the inverse. One of these questions should have asked me to find the inverse, so let's do that here, and then we'll evaluate these. All right, so to find the inverse of this function, we're going to swap the variables or solve for the other variable. Can't swap them since the letters have meaning, so we're going to instead take F equals 9/5 C plus 32, and we're going to be solving for the other variable, which in this case is C. So subtract the 32. F minus 32 equals 9/5 C. And then to divide by that 9/5, we're going to multiply by the reciprocal. So 5/9 times F minus 32 equals C. So C is 5/9 times F minus 32. Now evaluate and explain the following. So the g function is the name of the original function here. So I'm going to write this one more time in function notation. This would be F equals g of C equals 9/5 C plus 32. That just puts it not only in equation notation, but also in function notation. So we're going to do the same thing here. This will be C equals g inverse of F. F is the argument of the inverse function, so these do change. C being the argument of the original, F the argument of the inverse. That way we're able to express this in both function and equation notation. There we go. Now that we have the correct notation in here, since they're asking us about g of 45, g of 45 is going to be using the original function g. Will be equal to 9/5 times 45 plus 32. Let's see. 45 divided by 5 is 9, times 9 is 81, plus 32 gives us 113 degrees. The output is going to be in Fahrenheit. So what this one means is that 45 degrees Celsius is equivalent to 113 degrees Fahrenheit. And then in the next one, g inverse of 45. In the g inverse of 45, I'm going to use the g inverse equation. This would be 5/9 times 45 minus 32. Let's see, 45 minus 32 is 13 times 5/9. It's not going to come out evenly. So let me clear this real quick. We need to take 5/9 of 13. Comes out as about 7.22. Outputs are in degrees Celsius. So this means that 45 degrees Fahrenheit is about 7.22 degrees Celsius. Last, analytically prove that g and g inverse are inverse functions of each other. We're going to do that through composition. So let's show that g of g inverse of, the variable needs to go into g inverse first, so that variable has to be in Fahrenheit. So if I take the g function, 9/5 times, in place of the variable c, we're going to put in the other function here, 5/9 f minus 32 plus 32. So when we multiply, the 5/9 and the 9/5 are going to reduce and give me the f minus 32 plus 32, which is equal to f. And that's what it was supposed to equal because the input is what we got back out. And we do need to show this in both orders. So if we did g of g inverse, we'll also show g inverse of g. The argument of g needs to be c. So g inverse, 5/9 of, in place of the variable, we put the other function, 9/5 c plus 32. That all goes inside of f, then finish by the minus 32. In this one, our plus 32 minus 32 will add to 0. Then we've got our 5/9 times our 9/5 c. 5/9 and 9/5 multiply to 1. We come back out with just c, remembering that c was the name of the input, and that's what I got back out. So once again, confirms that these two functions are inverses of each other. The value plugged in is the value we got out when we compose the functions with each other.